Geotechnical investigations are performed by geotechnical engineers or engineering geologists to obtain information on the physical properties of soil earthworks and foundations for proposed structures and for repair of distress to earthworks and structures caused by subsurface conditions. This type of investigation is called a site investigation. Additionally, geotechnical investigations are also used to measure the thermal resistivity of soils or backfill materials required for underground transmission lines, oil and gas pipelines, radioactive waste disposal, and solar thermal storage facilities. A geotechnical investigation will include surface exploration and subsurface exploration of a site. Sometimes, geophysical methods are used to obtain data about sites. Subsurface exploration usually involves soil sampling and laboratory tests of the soil samples retrieved. Surface exploration can include geologic mapping, geophysical methods, and photogrammetry, or it can be as simple as a geotechnical professional walking around on the site to observe the physical conditions at the site. To obtain information about the soil conditions below the surface, some form of subsurface exploration is required. Methods of observing the soils below the surface, obtaining samples, and determining physical properties of the soils and rocks include test pits, trenching particularly for locating faults and slide planes, boring, and in situ tests. Soil sampling. Borings come in two main varieties, large diameter and small diameter. Large diameter borings are rarely used due to safety concerns and expense but are sometimes used to allow a geologist or an engineer to visually and manually examine the soil and rock stratigraphy in situ. Small diameter borings are frequently used to allow a geologist or engineer to examine soil or rock cuttings or to retrieve samples at depth using soil samplers, and to perform in-place soil tests. Soil samples are often categorized as being either disturbed or undisturbed. However, undisturbed samples are not truly undisturbed. A disturbed sample is one in which the structure of the soil has been changed sufficiently that tests of structural properties of the soil will not be representative of in situ conditions, and only properties of the soil grains, e.g., grain size distribution, Atterberg limits, and possibly the water content, can be accurately determined. An undisturbed sample is one where the condition of the soil in the sample is close enough to the conditions of the soil in situ to allow tests of structural properties of the soil to be used to approximate the properties of the soil in situ. Offshore soil collection introduces many difficult variables. In shallow water, work can be done off a barge. In deeper water a ship will be required. Deepwater soil samplers are normally variants of Cullenberg-type samplers, a modification on a basic gravity corer using a piston Lunn and Long, 2006. Seabed samplers are also available, which push the collection tube slowly into the soil. Soil samplers. Soil samples are taken using a variety of samplers, some provide only disturbed samples, while others can provide relatively undisturbed samples. Shovel samples can be obtained by digging out soil from the site. Samples taken this way are disturbed samples. Trial pits are relatively small hand or machine excavated trenches used to determine groundwater levels and take disturbed samples from. Hand, machine-driven auger. This sampler typically consists of a short cylinder with a cutting edge attached to a rod and handle. The sampler is advanced by a combination of rotation and downward force. Samples taken this way are disturbed samples. Continuous flight auger. A method of sampling using an auger as a corkscrew. The auger is screwed into the ground then lifted out. Soil is retained on the blades of the auger and kept for testing. The soil sampled this way is considered disturbed. Split spoon (SPT) sampler. Utilized in the standard test method for standard penetration test (SPT) and split barrel sampling of soils (ASTM-D 1586). This sampler is typically an 18-30 long 2.0 outside diameter OD hollow tube split in half lengthwise. A hardened metal drive shoe with a 1.375 opening is attached to the bottom end, and a one-way valve and drill rod adapter at the sampler head. It is driven into the ground with a 140-pound (64 kilograms) hammer falling 30. The blow counts hammer strikes required to advance the sampler a total of 18 inches. Accounted and reported. Generally used for non-cohesive soils, samples taken this way are considered disturbed. Modified California sampler. In the standard practice for thick-wall, ring-lined, split-barrel, drive sampling offsoils 1 ASTM D3550. Similar in concept to the SPT sampler, the sampler barrel has a larger diameter and is usually lined with metal tubes to contain samples. Samples from the modified California sampler are considered disturbed due to the large area ratio of the sampler, sampler wall area, sample cross-sectional area. Shelby tube sampler. Utilized in the standard practice for thin-walled tube sampling of soils for geotechnical purposes ASTM D1587, this sampler consists of a thin-walled tube with a cutting edge at the toe. A sampler head attaches the tube to the drill rod, and contains a check valve and pressure vents. Generally used in cohesive soils, this sampler is advanced into the soil layer, generally 6 less than the length of the tube. The vacuum created by the check valve and cohesion of the sample in the tube cause the sample to be retained when the tube is withdrawn. Standard ASTM dimensions are 2 inches. OD 36. Long 18 gauge thickness 3 inches. OD 36. Long 16 gauge thickness and 5 inches. OD 54 inches long 11 gauge thickness. It should be noted that ASTM allows other diameters as long as they are proportional to the standardized tube designs, and tube length is to be suited for field conditions. Soil sampled in this manner is considered undisturbed. Piston samplers. These samplers are thin-walled metal tubes which contain a piston at the tip. The samplers are pushed into the bottom of a borehole, with the piston remaining at the surface of the soil while the tube slides past it. These samplers will return undisturbed samples in soft soils, but are difficult to advance in sands and stiff clays, and can be damaged, compromising the sample if gravel is encountered. The Livingston corer, developed by D. A. Livingston, is a commonly used piston sampler. A modification of the Livingston corer with a serrated coring head allows it to be rotated to cut through subsurface vegetable matter such as small roots or buried twigs. Pitcher barrel sampler. This sampler is similar to piston samplers, except that there is no piston. There are pressure relief holes near the top of the sampler to prevent pressure buildup of water or air above the soil sample. In-situ tests. A standard penetration test is an in-situ dynamic penetration test designed to provide information on the properties of soil, while also collecting a disturbed soil sample for grain size analysis and soil classification. A dynamic cone penetrometer test is an in-situ test in which a weight is manually lifted and dropped on a cone which penetrates the ground. The number of mm per hit are recorded, and this is used to estimate certain soil properties. This is a simple test method and usually needs backing up with lab data to get a good correlation. A cone penetration test is performed using an instrumented probe with a conical tip, pushed into the soil hydraulically at a constant rate. A basic CPT instrument reports tip resistance and shear resistance along the cylindrical barrel. CPT data has been correlated to soil properties. Sometimes instruments other than the basic CPT probe are used, including a piezocone penetrometer probe is advanced using the same equipment as a regular CPT probe, but the probe has an additional instrument which measures the groundwater pressure as the probe is advanced. A seismic piezophony penetrometer probe is advanced using the same equipment as a CPT or CPTU probe, but the probe is also equipped with either geophones or accelerometers to detect shear waves and/or pressure waves produced by a source at the surface. Full-flow penetrometers T-bar, ball, and plate probes are used in extremely soft clay soils such as sea-floor deposits and are advanced in the same manner as the CPT. As their names imply, the T-bar is a cylindrical bar attached at right angles to the drill string forming what look like a T, the ball is a large sphere, and the plate is flat circular plate. In soft clays, soil flows around the probe similar to a viscous fluid. The pressure due to overburden stress and pore water pressure is equal on all sides of the probes, unlike with CPTs, so no correction is necessary, reducing a source of error and increasing accuracy. Especially desired in soft soils due to the very low loads on the measuring sensors. Full-flow probes can also be cycled up and down to measure remolded soil resistance. Ultimately, the geotechnical professional can use the measured penetration resistance to estimate undrained and remolded shear strengths. Helical probe test. Soil exploration and compaction testing by the helical probe test (HPT) has become popular for providing a quick and accurate method of determining soil properties at relatively shallow depths. The HPT test is attractive for in-situ footing inspections because it is lightweight and can be conducted quickly by one person. During testing, the probe is driven to the desired depth and the torque required to turn the probe is used as a measure to determine the soil's characteristics. Preliminary ASTM testing has determined that the HPT method correlates well to standard penetration testing (SPT) and cone penetration testing (CPT) with empirical calibration. A flat plate dilatometer test (DMT) is a flat plate probe often advanced using CPT rigs, but can also be advanced from conventional drill rigs. A diaphragm on the plate applies a lateral force to the soil materials and measures the strain induced for various levels of applied stress at the desired depth interval. In-situ gas tests can be carried out in the boreholes on completion and in probe holes made in the sides of the trial pits as part of the site investigation. Testing is normally with a portable meter, which measures the methane content as its percentage volume in air. The corresponding oxygen and carbon dioxide concentrations are also measured. A more accurate method used to monitor over the longer term, consists of gas monitoring standpipes should be installed in boreholes. These typically comprise slotted UPVC pipework surrounded by single-sized gravel. The top 0.5 meters to 1.0 meters of pipework is usually not slotted and is surrounded by bentonite pellets to seal the borehole. Valves are fitted and the installations protected by lockable stopcock covers normally fitted flush with the ground. Monitoring is again with a portable meter and is usually done on a fortnightly or monthly basis. Laboratory tests. A wide variety of laboratory tests can be performed on soils to measure a wide variety of soil properties. Some soil properties are intrinsic to the composition of the soil matrix and are not affected by sample disturbance, while other properties depend on the structure of the soil as well as its composition, and can only be effectively tested on relatively undisturbed samples. Some soil tests measure direct properties of the soil, while others measure index properties, which provide useful information about the soil without directly measuring the property desired. Geophysical exploration. Geophysical methods are used in geotechnical investigations to evaluate a site's behavior in a seismic event. By measuring a soil's shear wave velocity, the dynamic response of that soil can be estimated. There are a number of methods used to determine a site's shear wave velocity. Crosshole method, downhole method with a seismic CPT or a substitute device, surface wave reflection or refraction, suspension logging, also known as PS logging or OYO logging, spectral analysis of surface waves (SASW), Multi-channel analysis of surface waves (MASW), refraction microtremor (REMI), other methods, electromagnetic radar, resistivity, optical, acoustic televiewer survey. Topic. See also: Geotechnical engineering, engineering geology, geotechnics, Nippon screw weight system, soil mechanics, soil test.